Kinematics. We discussed Newton's law of gravitation, and Newton's law of motion. Right? This is what we had. I'm going to use a red one.
You can give it to me.
What we had in last class was something like this. We had a reference frame. We said this was our inertial reference frame. Okay. Reference frame, inertial coordinate system, which means it is non-accelerating, non-rotating. Yeah. And we have another frame. Okay. Which is small ijk. This distance is this vector is, what did you say this vector was? R0. And we're talking about relative motion of a point P. Okay. This is R, right? This is R relative. square equals V naught plus V relative plus omega. Did we use capital omega? Omega naught. You have to understand this relationship. Okay? For any vector, this is a sign. For any vector A, d over dt of A is equal to the local derivative. We will represent this by A circle bar. Okay? Sometimes we use the A circle bar plus omega cross with A. Okay? So what this means is, if you have a vector A, coordinatized in any plane, okay? I, J, K. If you want to take the derivative of this vector, it will be the change in the vector, change in the length and direction of this vector, as seen in this coordinate system or this reference plane. Now, if this reference plane is not not inertial, then this applies. Okay? Have to keep that in mind. Think about this as the position, your position or your orientation in a moving plane, moving aircraft. Right? Your position or your orientation in an aircraft. Let's say you are traveling from one airport to another, or one city to another. Now this vector is changing. Your position with respect to the aircraft itself is changing, right? But this reference frame, which is the aircraft reference frame, that could be changing as well, right? It is changing. That's not an inertial reference frame. So this applies the rotation of this reference frame with respect to an inertial reference frame. Got it? Right, this is a non-inertial reference frame. Since you have to, your Newton's laws apply only in an inertial reference frame. Now, if you want to define the motion, your position of orientation, which is expressed as A, and see how the force is affecting that. You have to understand the motion in an inertial reference frame. Okay? Make sense? This is for any vector. Keep in mind. So we'll apply the same thing again here. Alright? So if you want acceleration now, how do you do acceleration? See, I've just applied the same for this. Keep in mind this, okay? How do you define acceleration? acceleration would be, look at this, okay?
Dr. Sunny, do you have the keys to the control lab?
Not here, it's in my office. So this would be V over dt into V plus V cross with, sorry, omega cross with is R naught plus R relative d over dt of R. See, just apply this. Okay, we'll apply this. So what is d over dt of R? It is R circle dot, right? Plus omega cross with this is this, okay, and this is this. Make sense?
So, R naught equals V dot.
R circle dot. Circle dot means local derivative. Okay. So what you do is, see, you have this, right? You're just going to substitute what R is. What is R? R naught plus R relative, right? You have circle dot plus omega cross with R. Okay. This is this. Okay. What is this? R relative. So you see, just look at this. You have this. This translates to this one. You can forget about this for a while. So compare this one and this one. R, I have represented R naught, the local derivative of this is this. Plus this is this. Correct? Omega cross with R naught plus R relative. So how does this, if you have a cross, you just cross this and you cross this. Okay? This is essentially 0. Okay? This and this, they are the same thing. R naught is not changing. If you're looking at omega, if you're looking at R naught, this is not changing in this, regardless of how this rotates. This does not change. Okay? So this is 0. But this, you see, Now you do the same thing for acceleration. So acceleration is equal to, or if I do d over dt of v, what did we say this was? We'll use this, yeah, we'll use that. V circle dot, okay? So now what I'm going to do is, I'm just going to substitute whatever is in here. So let's look at this. We have V naught plus V relative plus omega cross with R relative. This would be how would you handle this? Cross the, what did we say about the derivative of a cross product? Antoine? Plus V relative, sorry, plus omega all square E naught plus V relative plus omega cross with. Yes. Yes. Huh?
The omega cross product of R relative, that dot over the omega or the R relative. The one
So
of
this one, right?
yeah, what is that dot supposed to be?
Yeah, I'll get to that. So what did we say the derivative of, what is d over dt of A cross B? Huh? Remember? A cross with B dot plus, sorry, minus B cross with B dot. So check your notes. I think we have done this. I'm sure we have done this. Okay? A dotted with B, d over dt of A dotted with B is just A dot B dot plus B. No. So we want to apply this over here. It's getting confusing. So what you have here is, on the left hand side, you have acceleration A is equal to V dot, V circle dot, okay, or V naught circle dot, V relative circle dot, plus, so what are you going to get here? Omega cross with R relative circle dot minus R relative cross with omega circle dot. Okay. Plus omega cross with omega plus omega cross with V relative plus omega cross with omega cross with R relative.
Okay, I have a question.
Hmm.
My question is,
So what I did was this crossed with this.
I understand that, I'm talking about the whole purpose of how you come up with that based upon what you did previously, how did that come about?
This one?
No, the one that you were at.
So you understand, you have to follow this rule always. Okay? So we apply the same rule for this. If you want to take a derivative of this, it would be the circle or local derivative plus omega into r first. And what we did was we just substituted for r, vector r, which is this plus omega cross with again those two. And we split this open, right? This is here, this is here, omega, so this is 0. So we just end up with this. Okay? Now we apply the same thing to velocity. So what is d of velocity? d over dt of velocity? It's local derivative plus omega cross with v. Now again we substitute for v. It is this whole thing, right? That is this plus this omega cross with this again this whole thing. And now we are splitting these terms again. So you have this, which is here, this, which is here. The derivative of cross product is, we have to apply that rule, right? So you have this minus this, plus omega cross with this, omega cross with this, omega cross with, okay? There is something very important here. That's the reason I'm discussing this. And you have to know why we are discussing this. And this will also answer your question as to why we are accelerating when we are orbiting something. When an orbiting body you guys told me, right? We are moving at a constant velocity. You thought we are moving at a constant velocity. And I said, no, that is not true. Correct? So we have to understand why that is not true. Most of the intuition is that we are moving at constant velocity. You're okay, Sammy? You guys are, is it obstructing? Dion?
Yeah, but it's cool.
Okay. Let's summarize what we have. Let's gather all the terms, okay? So these two, it will just be acceleration is equal to A circle dot plus A relative, right? Can we group these two terms together? It's the same thing, right? So 1 and 1. It's the same thing. It's 2 into omega cross with V relative. You with me? Hmm? omega dot cross with simple cross with relative plus omega cross with so have you captured all the terms? This one is missing. This one we have captured as, if we change this, see A cross B, what is A cross B? Minus B cross D, right? And that's what we have done here. Okay. So what is missing? Is anything missing? Omega cross V naught is missing. What happens to omega cross V naught? You see, we said this term is 0, right?
Yes. So actually it also be zero.
This term would also be 0. Okay? Because, see, this is not changing. Okay? So this term would also be 0. Now you have this, you have this, you have this. So, if you look at what these terms are, this is the Coriolis acceleration. See, this acceleration we are talking about, you can we're talking about So you have a central body. Okay? Let's say you have a orbiting body. This is the position of that orbiting body, and that is what we discussed, right? This P is a particle or a orbiting body. So you have a component, a radial acceleration. You know what radial acceleration is? You're trying to see if you have you tried to spin, put a weight on a thread and try to rotate it. Huh? It tries to pull you, right? And there's a force which keeps it. So the string force keeps it in, but it's also trying to go away. And there's acceleration going around. So the tangential acceleration, use what you're seeing here is, I'll give you the exact terminologies for these terms. Write it down, or take a snap, Photoshop, take a picture of this. I'll give you the exact terms. But what this entails is the radial acceleration, the tangential acceleration. You know what Coriolis acceleration is?
Not Coriolis acceleration, no, it has something to do with rotation.
Right. So when you're talking about acceleration, what are the, you heard about the centripetal and the centrifugal force? It is also a kind of acceleration. So centripetal and centrifugal are opposing, right? So when you're doing that, the centrifugal forces trying to throw you away, trying to push you out. The centripetal is, the centrifugal force is, right, trying to pull you away. The centripetal is trying to keep you in. So there's a centripetal component, there's a radial component, there's a tangential component. We'll take a look at all of those components in I'll just give you what those components are in this. Okay? See, you have to try to appreciate what mathematics does for you. Here, these accelerations, Coriolis acceleration, centripetal force, centrifugal force, they came about as intuition. Like, when people did that, they felt that there is something else going on than what it's not intuitive actually, it's counterintuitive. People who could realize that thought there is something else going on, there is some other acceleration. So this Coriolis acceleration is named after Coriolis. So it's actually Gustave Coriolis, okay? And these terms, what you should realize is, they can be very easily seen when you apply basic mathematics. Yes, you.
What is, I still don't understand, like, what is the principle behind it?
I'll explain what the different accelerations are. But for now, just understand the mathematics. If you do mathematics is very systematic, right? Very methodical. If you understand mathematics and apply it correctly, you will end up with the correct terms. Okay? You will not go wrong. But if you try to debate, if you try to figure out if this is correct, if this is not correct, then you may not get all the terms. So try to understand this when we are dealing with orbiting bodies. We are not dealing with simple linear velocity and linear acceleration. It is much more than that. And this is how you get to any acceleration, this is all kinematics. And if you know this kinematics, you should be able to do any kinematics. Okay. Next class we'll start with the two-body problem. We'll start with chapter 2. Any questions so far?
I wasn't sure how you wanted to I'm for the stapling together or.
Yeah, you can staple and give it to me. Excuse me, Mr. Jones, can you keep your attendance?